the elements are going to be, elements now are classified. Now you say here, you understand, this is going to be S block element, P block element, D block element, and F block element. The Hobba principle gives you, helps you to identify sodium, S block element. You know the answer. What is the electronic configuration of sodium? 1s2, 2s2, 2p6, 3s1. Where does the last electron go to? S orbital. So S block element. S block element. Let me take sulfur. Atomic number is 16. Write it, write it, write it. You should know now. 1s2, 2s2, 2p6, 3s2, 3p. Where does the last electron, 16th electron, enter into p orbital? Therefore sulfur belongs to p block element. Sulfur belongs to p block element. Iron, 26th electron enters into the d orbital, therefore d block element. In that period, third period, I told you, atomic number 21, scandium, I told you, 22, 23, 24, 25, 26, 27, 28, 29 and 30. Up to this, all of them are called D block elements. D block elements. D block elements. Why are they called D block element? Because the last electron enters into the D block. Up to 20, what is the electronic configuration? I told you 4s2. What should be the electronic configuration of 21? 4s2, 3d1. Isn't it 3d next to orbital? 3d2, 3d3, 3d9, 3d8, 4s2, 3d8, 4s2, 3d10, 4s2, 3d10. Isn't it? So, and F orbital, F block elements. If any periodic table you see, the lanthanides and actinides, F block elements. And the last electron enters into the F orbital. Now you know, given an atomic number, isn't it possible for you to identify which category it belongs to? Atomic number 57. You write the electronic configuration. Find out where that's. I am not asking you to write now. I am just giving you. Now I will give you atomic number 22. Write 22. Easy. Now you should, without writing, you should be able to tell me. D block element. D block element. 20 up to 20 is this. 21. Anything greater than that 20 is going to be 3D, 3D1, 3D2, D block element. Atomic number 35, P block element. What is that element? Bromine. Bromine. Atomic number of fluorine 9, fluorine 9 plus 8. Soliya, 9 plus 8, 17. Bromine 17 plus 18. Oh, you didn't bring the calculator today. 35. Iodine is going to be plus 18. 53. All those last electron, all those elements, the last electron enters into the p orbital, p block elements, s block elements, group 1 and 2. Alkali metals and alkaline earth metals only. Lithium, sodium, potassium, rubidium, cesium, francium. We have only 6 elements, include hydrogen also. Hydrogen also is placed in the first group as well as this alkaline metals. So how many elements are there? The group 1 here, 7 elements including the hydrogen atom. The hydrogen is only exception. In what way hydrogen is exception? Group 1. There are many exceptions. Hydrogen is the only element which is a gas. All the other elements are solids and liquid. Which is the liquid element? Group 1. Cesium, I told you. Cesium is a liquid, gallium is also liquid, 2 metals which are liquid, mercury is a liquid, okay, and all the other elements are solids. Hydrogen is the only non-metal. All the other metals, all the other elements are metals. What is the similarity between hydrogen and the rest of the elements? What is the similarity? Hydrogen has got 1 electron the outermost shell. All these elements have got 1 electron outermost shell. And what is the general electronic configuration of I gave you today a question here. In fact, the answer must be for the halogen, the general electronic configuration of halogen. Just as you write general electronic configuration, group 1 is NS1. What is 1s1 stand for? Hydrogen. 2s1 stand for lithium. Then you have lithium, sodium, potassium, rubidium, cesium, francium. NS1. And what should be general electronic configuration? NS2. NS2. The first orbital cannot be 1s2. 1s2 lies here, helium, group 18. Helium. Isn't it? There is no element above the second period. What is the first element in the second period here? Beryllium. Please recall the periodic table. Periodic table, the position is very important for you. And from that I know the atomic number, from the atomic number I get the electronic configuration, from the electronic configuration I am able to get the number of unpaired electrons, from the number of electrons the entire array of chemical properties. Whether it is a metal, whether it is a non-metal, electropositive element, electronegative element, what should be the nature of the oxide, what should be the nature of the hydroxide, is it a strong base, everything is known. And for that you must know that NS2 configuration. Okay. What is the first element for the NS1? Hydrogen. What is the first element in the case of NS2? It's beryllium. Beryllium. Okay. P block elements. The next one, yeah, P block element. The P block elements start from group 13 up to group 18. 13, 14, 15, 16, 17, 13, 14, 15, 16, 17, 18. It starts with boron here. We already wrote the elements in group 13. Boron, carbon, nitrogen, oxygen, fluorine, neon. This we know. Boron, aluminium, gallium, indium, thallium. Fill in protein. You are waiting for my question, is it? I thought you should have finished by now. 14th element, 15, group 15, group 16, group 17, group 18. Can you guess? Carbon, silicon, germanium, tin and lead. Eka aluminium, eka silicon, you would have எங்கேயோ கேள்விப்பட்ட மாதிரி இருக்கு. Eka aluminium, it was not known, but he left an empty space in Mendeleev's periodic table. Is another familiar term that we have heard, Mendeleev's periodic table. He left a space over here, but he did not know it is going to be gallium. He called it as Eka silicon. Later on it was found to be germanium. This comes in the competitive examination. Which of the following is identified as Eka silicon? They give you 4 answers. One of them is going to be germanium. Nitrogen, phosphorus, arsenic, antimony and bismuth. Who have already written it? Raise your hand. Very good, right. And should I ask you this? Wonderful. Polonium, radioactive. All of us know this. All of us know this. Fluorine, chlorine, bromine, iodine. You knew this because you have been repeating it. If you are going to repeat the same thing, 1/2 of the periodic table, you know, you have memorized it now. We know the first group, second group also, S block element. These are all called P block elements. P block elements. D block elements, group 3 to 10. We just wrote it, group 3 to 10. Atomic number starting from 21, D1 to D2, D10. What is the D10? 3D10. What is 3D1? Scandium. What is 3D10? Zinc. At least let us write group scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel as a triad. Iron, cobalt, nickel, copper and zinc. Copper and zinc. You don't need to know the F block elements. They are called F block elements. Why are they called F block elements? Because the last electron enters the F orbital. Yes, you wanted to. Do you still remember your question you wanted to ask me, or you forgot? What is it?
You have written the 3P4, sir. For oxygen, sir.
Yes.
Why did it have 2, sir?
3P4, oxygen. Yes? I said 2.
You have written it had 2 unpaired electrons, sir. But it ended with 2P4, sir.
Wait. Oxygen is going to be 8. Did you ask for the oxygen or sulfur? Oxygen. There are only, why, how come the 3 third level? It is only 2, 6. 1s2, 2s2, 2p4. There is no sulfur. You get 1s2, 2s2, 2p6, 3s2, 3p4. Therefore, you see here the general electronic configuration is ns2 np4. ns2, in future you have to say general electronic configuration of halogen ns2 np5, write it. ns2 np6 belong to group 18. ns2 np1, isn't it? Yes. ns2 np3 ns2 np1, ns2 np2, ns2. This is the general electronic configuration of these elements. Yes, now tell me. Oxygen is going to be 2p4 and it is completely filled, 2 electron, no unpaired electron. P orbital, we have px orbital, py orbital and pz orbital. Of the 4 electrons, each one go and occupy the 1 electron here. Any one of the 3, 2, 3, and the 4th one can pair with any one of them, either here or here or here. For the sake of convenience, we just tried. Therefore, we say there are 2 unpaired electrons. Making use of the Aufbau and Hund's rule, making use of Hund's rule, 2 unpaired electrons. Okay. Same way in the case of sulfur also, 3s2, 3p4, 2 unpaired electrons. Not only sulfur, in all the elements, ns2, np4, 2 unpaired electrons. I can ask you which one of the following elements has got 1 unpaired electron, and obviously this could be one answer. Along with that, I could have given you any other 3 answers: aluminum, germanium, selenium and chlorine. Which of them following has got 1 unpaired electron here? This is going to be one. Tell me. Wait. I have made a question here. Which of the following elements have got 1 unpaired electron? I told you aluminum. Answer A is aluminum. Answer B is going to be phosphorus. Answer C is going to be selenium. Answer D is going to be bromine here. Which of these elements have got 1 unpaired electron? What about aluminum? ns2 np1. ns2 is paired, 1 electron the p orbital. Therefore, there is ground state configuration. You should always write the ground state configuration. 1 unpaired electron here, 1 unpaired electron here. As per the Hobba principle, you have to write this Hobba principle ladder, increasing order of energy levels. But aluminum, that is going to be a different question. We are going to explain it. I purposely left a few elements while writing the electronic configuration. I left boron, carbon, silicon. I left boron, carbon and silicon. I went straight away to conveniently to nitrogen, etc. Beryllium and boron. Beryllium also I left it. Okay, is that clear to you? Exceptions to Hobba principle. I am going to take up chromium 24 among the D block elements, exception to Aufbau principle among D block elements. Two elements are there in the third period, namely chromium and copper 29. Now, as per the Aufbau principle, 4s2 3d 4 up to 4s2 I told you 20, up to 4s2 20. What is the next energy level? 3d, so 3d4. Now, I have to tell you another important aspect here. How did you write for iron here? Iron you wrote as per the Aufbau principle 4s2 up to 4s2 20, the remaining 6 electron go to this. After having written this electronic configuration as per the Aufbau principle, you have to write the electronic configuration henceforth as 3d6 4s2 only. We have to revert it. This is only for you to know the electronic configuration. After writing this, in order to account for all the chemical properties, how many electrons are lost, how are you going to explain the divalency, trivalency, tetravalency, etc. immediately, because electrons are always added and removed from the last main energy level. This is the main energy level, please remember that. The fourth shell. If you want to remove an electron, electrons must be removed. That is only for us to write the electronic configuration. This discrepancy is going to be explained later on in the quantum chemistry, quantum mechanics. Okay. Now, after writing this, writing the electronic configuration henceforth you must say it as 3d6 4s2. You should not say it 3d 4s2 3d6. Same way, what about the electronic configuration of chromium? It is going to be 3d4 4s2, 3d4 4s2. What are you going to say the electronic configuration of copper? What is going to be electronic configuration of copper? As per the Aufbau principle? Tell me. Up to 4s2, how many electron? 20 electron. How many more? 29. Atomic number is 29. Please remember, atomic number 29. As per the Aufbau principle, 4s2 3d9. But you are going to write this as 3d9 4s2. Okay. Now, we are going to see the exceptional behavior of copper and chromium. Copper and chromium. Copper, the electronic configuration of chromium is going to be, instead of 4s2 3d4, it is going to be 4s1 3d5, or it must be written as 3d5 4s1. As per the Aufbau principle, we have written this. So, what is the electronic configuration of chromium? 3d4 and 4s2, but modified Aufbau principle. We are going to use modified Aufbau principle. Modified Aufbau principle. Why do you want to do that? Because the electrons have to be removed or added only from the last shell or to the last shell only, last main energy levels. Therefore, I have written this. Similarly, what should be the modified Aufbau orbital structure of the copper? Instead of 3d9 and 4s2, we are going to write this as 3d10. Take one electron there. Here, take one electron, uncouple it and promote it to the d orbital. Only in these two cases. Only in these two cases, not the other cases. Because the stability of an atom, either it should be completely filled orbital, it should be completely filled orbital. That is what we saw in the case of the rare gases, helium, neon, argon, krypton, xenon, etc. All the orbitals are completely filled. The next one in the decreasing order of stability, exactly half filled orbital exactly half-filled orbital. S orbital 1, P3 is half-filled, D5 is half-filled, F7 is half-filled, because maximum number is 14, half of that is 7, maximum number is 10, so D5, maximum number is 6, so P3. Now, for the sake of convenience and for the reasons known to us, we are going to exclude this S1 orbital. It is not to be considered as half-filled orbital at all, though in terms of the arithmetic the maximum number is 2, half of that is 1, it is taken. There is no stability, we will come back. When I say half-filled orbital, it is always with reference to the p orbital, d orbital and f orbital. P3, d5, f7 is going to be more stable. Therefore, copper changes the configuration. Instead of 3d9 4s2, 3d10 4s1, 3d10 is completely filled, it is going to be completely filled. Therefore, it prefers to occupy this orbital structure. And take the chromium here, 3d4 4s2, by taking one of the electron, uncouple that electron and is taken to the d4 here, it becomes 3d5, 3d5 becomes half-filled here, therefore it is more stable, the electronic configuration of this. And all the other properties have to be explained based on the modified Aufbau principle,